So I'm going to be doing Fluent Project 1 for Laminar boundary layer airflow on a horizontal thin plate. This is Alexander Powell, and we are going to begin here with some geometry. We're going to create this geometry in Design Modeler. Found this one to be the easiest one to use. Alright, so we're going to be first we got to get these units into inches. The flat plate is going to be 0.1 inches thick, 6 inches long. We are going to create this on the XY plane. We're going to do a corner rectangle. We're going to start at the origin. Then we're going to dimension this guy like this. And then we're going to do another dimension like this. So L1, it's going to be 6 inches long, and it's going to be 0.1 inches thick. Done with that. Now we are going to create another sketch, another rectangle. This one is going to overlap this one, and this is going to be where the air is going to flow. We got to create some more dimensions here. First is going to just be the general length of this, and then how far away it's going to be from the y-axis, then how thick it'll be, and then how far away it'll be from the x-axis. So I'm going to make this 15 inches long. It is going to be 5 inches to the left of the y-axis. This is going to try and center it, since this the flat plate, I didn't center it on the origin. I'm going to make it 8 inches thick and 4 inches from the x-axis. There we go. So we have these two all set up. Now what we can do is, we're going to come to sketch 1. We are going to create a surface from a sketch, and we're going to make it frozen. This is so when we make surfaces for both of these sketches, they don't overlap. They are their own separate bodies. We're going to generate that. Sketch 2, we're going to do the same thing. Surface from sketches. Frozen. It's going to be frozen here, then we're going to generate that. Then we got to create a boolean, and that's what we're going to do here is we're going to remove the flat plate surface from the bigger rectangle here. Subtract. And then tool body is going to be surface sketch 1. Got that. So I believe actually we got to do it like this. Here we go. And then this one's going to be this body. Can generate that. There we go. So this is going to be our finalized geometry here for the flat plate. So we can X this out now. That'll save, and now we're going to do a fluid flow Fluent analysis. We're going to bring the geometry over, we're going to share it, and now we're going to create our mesh. Alright, so now this is the important part. We need to create a good mesh that will be able to analyze the flow of the air very precisely over the top part of the plate in specific. So the first thing we're going to do is we're going to do the all triangles method over the entirety of the geometry. Then we're going to do a sizing mesh, and that's going to be on the edges of the flat plate. This is going to help kind of add some denser mesh around all the edges here. This last edge is always give me a hard time. So those 4 edges here, we're going to do an element size of 0.1. And then last part of the mesh, we're going to do some inflation, and this is going to really make the mesh dense above the top part of the plate. So this boundary wants to be the top part. Do a first layer thickness one of 0.01 inches. do maximum layers 50 and the growth rate of 1. We're going to generate this. Alright, you can see. So we have a decent mesh around the entirety of the plate. It's a little bit more dense around all the edges, and on the top edge specifically we have a very dense mesh, and that's going to really help us see the characteristic of the boundary layer. So we'll update this into Workbench. Can X this out. Now we'll go into Setup. Solver processes, we'll go to 4. Alright. Some important things to do in the setup before we can solve. So it loads up here. You have to make sure that the air has, this is going to be on sea level, so we have to make sure we're at 1 atmospheric conditions for the airflow. Oh, actually, one thing we need to do here, we're going to have to actually go back into the mesh. There's an important step we have to make sure we have here in the mesh. So it loads back up. What we have to do is we have to make named selections for the entire geometry here. That's going to be important for setting up initial conditions. So go to edge select, pick this guy. This is going to be name selection. This is going to be the inlet. This is where the air will flow in. This will be the outlet, and of course this is where the air will flow out. We're going to select these two edges. This is symmetry here. Alright. Now I like to select each of these individually. So this will be top wall. Then this guy is going to be front wall. This guy will be bottom wall. And this guy will be back wall. So now we know the air, it's going to be hitting these parts of the walls, and that's important for the analysis later. Make sure everything's labeled correctly. You can click these and it'll show what each one is. Alright. So we can update this. And now we are good to go to move on to Fluent. So we close this out. Now we can go back up into Setup. Update the mesh. Same thing here. Alright, so for this part of the project, I will be doing the 15 meters per second free stream velocity. And so we're going to need to do a few things. We're going to have to be able to plot the velocity profiles at the midpoint and at the end point. We have to plot the variation of wall shear stress along the flat plate, plot the variation of local skin friction across the flat plate, and then get the drag force coefficients for the flat plate, as well as get velocity contours and velocity vectors on here. Alright, so important things. We're going to set this to laminar since it's going to be laminar flow. Can do that here. Materials. This is going to be air. So yep, this is all correct. The density of air at this sea level is 1.225, and the viscosity is 1.7894 times 10 to the negative 5. So that's all good. So now we need to go into the boundary conditions. The inlet here, this is important. So we need the velocity magnitude to be 15 meters per second. Now we can check the outlet. We want to make sure that it's going to be sea level air pressure, and that's the gauge pressure of 0, which is good. So we're all good there. There's going to be a couple report definitions we want to do. We want to do a force report for the drag coefficient. And we'll just name this drag coefficient for 15 meters per second. And this is going to be mainly we want on the top part of the wall there. So we can just hit OK. And we'll do another one. We can do this for the drag force for some comparisons here, also along the top part of the wall. And this will be force drag 15 meters per second. And then we'll just do OK. So it'll compute those now. And after that, everything should be good to go. So we'll run the calculation. It's going to initialize it for us. I'm going to do 500 iterations just for the sake of the video so it doesn't take so long. Calculate this. It's going to initialize. You can see here, this is the force drag, the drag force plot. It's also going to do a scaled residual and then also the coefficient, the drag coefficient plot. So once it gets through these, there's a couple plots that we have to do in Fluent, as the option's not there in CFD post, and that will be the skin friction coefficient. As well, we can compute the drag force coefficient while we are here. As we end up, we can see some basic contours just to see what it looks like, but we'll want to do the full thing here in CFD post. So we can compute this display. You can kind of see a basic image of the fluid flow there. Alright, but so one thing that we can do here is we need the drag coefficient. So we're going to do it over the top wall. We can compute it here. Drag coefficient on the top wall is 0.04335. And then we'll have to compare that to a theoretical value. As well, we are going to do a plot of the skin friction coefficient. So I'll just name this CF. And skin friction is going to be in wall fluxes, skin friction. And we'll do this along the top of the wall. Save and plot that. So this looks to be the skin friction coefficient along the top part of the wall. Actually change this so we can kind of see how it changes as it goes along the top part of the wall. But now that we are finished with that, we can go back into here and go into the results. And here's where we'll be able to plot the laminar boundary layer velocity profiles at the 2 points. And this is where it's going to be helpful that we set up the flat plate at the origin. So easy thing to do is we can look at symmetry 1. Symmetry 1 is actually the front part of the plate here. So a lot of what we want to do, so the first thing we can do is we can do the contour map. This will be velocity contour. We're going to set this to velocity. We'll do this. Location, we want it to be symmetry 1. That's going to be that front symmetry there so we can actually see the fluid flow. We're going to do 101 contour so we can see a little bit better. And then we can apply that. So yeah, we can see the fluid flow. You can see where it comes up. Creates kind of that boundary layer shape. Now we are going to do a velocity vector one. Locations also on symmetry 1. And we make this 0.2 so we can see some more of them. We can hit apply. We'll turn off velocity contours. And now we can see the, you can kind of see the profile actually. So it comes here, you can see that parabolic profile. Now what we want to do is we want to add a couple line locations. This is so we can create that velocity profile. So we're going to name this one the midpoint. Now this is in meters, so we have to convert 3 inches to meters by multiplying by 0.0254. So we're going to be at 0.0762. 0.2 is also going to be at 0.0762. And now this part is kind of, we need to see about how high up it's going to go, the line. And we want 50 samples for this. Alright, so you see it was a little too high. I believe this actually has to be about there. We want it to be a little bit higher to where it looks like it gets into the free stream velocity part. So a little bit higher. Alright. So that's what we want the first line to be. 50 samples, good. Now we can create another line here, and this is going to be at the endpoint. Same thing, except now we're going to be at 6 inches, which is 0.15254 meters. 1524. And this is also going to be at 0.1524, except now this is going to be at 0.006. 50 samples. This is to kind of make the line a little bit more precise here, and we can see the other line there over there. So now we can do the velocity profiles. So we're going to want to plot here. This is going to be velocities. Data series, we're going to name this one midpoint, and then we're going to add at location midpoint. And this is going to be endpoint velocity at the location endpoint. X-axis will be the velocity, y-axis is just going to be y, and now we can apply. See here, there was some variation. But it does kind of reach that, it goes past the 15 meters per second, but it does start reaching that free stream velocity as you get closer and closer to 0.006. And it follows a similar Blasius velocity profile line where it comes up to that 15 meters per second as it reaches the free stream velocity. And now we can plot the variation of wall shear stress as well. So we can do this. This is going to be shear stress. This will be a scatter this time. Location on the top of the wall. X-axis, we're going to want to do X. That's just going to go along the top of the plate. Y-axis is going to be wall shear, and then we can apply. And then we can kind of see the shear of the wall here, and you see it's going to be a little bit at the trailing edge and the leading edge. There is a good amount of variation there because of how the flow interacts with the front part of the plate and the back part of the plate. So this here would be the wall shear stress along the plate. And then what we can actually do, go back in Fluent, so I do not forget here, is we can go into that coefficient of drag and compute it. Oh, I believe I did do that, and that's where it is, 0.0433. But after all this, we can export all this data into Excel, tabulate it, compare it with the theoretical values, and this is about going through the project here. We'll calculate the Reynolds numbers in Excel and prove that it's laminar. We got the velocity contours zoomed in, velocity vectors. We plotted the boundary layer velocity profiles. And actually from these profiles here, we can estimate. So it looks like boundary layer is about 0.005 meters from this simulation. And I'm getting that. That's about where the velocity approaches that free stream velocity. And we know that the boundary layer thickness, the velocity is 0.99 of the free stream velocity, or about the free stream velocity. So it looks like at about 0.005 meters, we are reaching the boundary layer thickness. We plotted the shear stress along the flat plate here. You can kind of see the variation at the leading edge and at the trailing edge. We plotted the skin friction coefficient along the flat plate here, saw its variation, and we calculated the drag force coefficient. And so that's what we had to do in Fluent for this project. Thank you.